Okay, then take derivative of sine. What's derivative of sine? So times cosine, and then keep the inside of the sine function intact. Hopefully that makes sense. Now we're going to focus on the cosine. What's the derivative of that? So times negative sine, and keep that inside intact. And then lastly, this one here, times 4. If you want to clean it up, you have -8 to the left and all that other junk there, then you're done. Yeah, so 19 would be a triple chain. But the exponent, because you have sine squared. Yep, that's exactly what they have. Um, yep. Okay. Wait, the sine squared? Wait, what? No, it is. No, this right here. We have this right here. It's the same thing as this. The whole thing is squared. It is. Yeah, it's a notation thing. The whole thing is squared. And that's okay if you're confused about that because you haven't really seen that notation, but the whole thing is squared. Yeah. Yeah, so that's a triple chain. Right. Yeah, I'd say 19 is probably the hardest one in that set. 15. 15 I would just call I think it's a double chain. So f prime of x, do the 6 in front, drop the exponent by 1, keep the inside intact, right? Then multiply by the inside, do it in red. So what's root of 1? Plus, now this is tricky because that's actually a chain rule within itself. So if you have cosine squared x, right, we'll just do it off to the side. That's the same thing as saying this, right? How do you do that derivative? What would you do? So 2 cos x and then times derivative of cosine, which is what? So you bring it back into the mix. So -2 sine x cos x. And the final answer should be -12, 1 plus cos squared x raised to the 5th power times sine x cos x. So yeah, I mean that was a double chain because you had to do another chain rule within the chain rule. Yeah, that's what they have. And by the way, I didn't assign the even, so I think that would be a good opportunity to do more practice with this, especially we're going to do this with logs and exponential functions. So yeah, by the end of this week, you should feel more comfortable with chain rule. Um, okay, anything else on homework? We're good? Okay. So I do want to wrap up the notes. So if you guys get your notes out, I want to do that last page. I want to talk about why we use radians for a derivative of trig functions. And I have a new set of notes we're going to move into. And I have it all on the couch over there. So let's finish off the notes. Okay. So last time we said that the results for trig derivatives were only valid. Well, actually, I never really said that, but I'm telling you now. When you're in radian mode. And the reason why is because when we did all these like other derivations with all these limits, like sine h over h, whatever, the assumption is that these limits only work when you're in radians. So when we actually went through the formal derivations and we use these extra limits as part of that derivation, I probably don't remember, but when we did do that, um, the assumption was that h is in radians. And if we look at the graph of phi equals sine x and its derivative in radian mode and degree mode, we get the following results. So for example, I'll go to could do some Desmos. Because the TI for calculus is a little clunky. So let's see here.
My sister's.
So y equals sine x. And by the way, you can always switch to if you go to that little toolbar, you can always like change this to like 2 pi to 2 pi. And that's a pi over 2. However you want to do it, right? And of course, I'm in radian mode, right? And then if I do dy over dx, 1. We call this f of x. There we go. Desmos seems like that better. So yeah, so you have that, right? The blue curve. Now, what if I switch this to degrees, something weird happens, right? Because it has to go from negative 360 to 360. But notice the blue line looks flat. Why do you think it's doing that? Well, let's go back to notes and let's actually do this when it's in degree mode. If you think about it, how do you convert degrees to radians or vice versa?
I ever 180.
Yeah, exactly right. Yeah, right. And that gets you radians. So that's what I'm going to do here. We have y equals sine x degrees, y equals sine, and that's going to be pi over 180 times x. Now, if I take my derivative, what's that going to be? Negative cosine. Keep the inside intact, and then what are you going to multiply after that? Yeah, exactly. So it's clearly a very different function. Also, the period changes as well, right? You guys remember how to find period? So the amplitude's low. How do you find period? 2 pi over what? So if I do 2 pi or pi over 180, clearly what's my period? 360. Yeah, as it should be, right? So that's why you get something really weird if you do this in degree mode. So degree mode almost has like no place in this class. So make sure you say, if I do any derivative questions that you guys involve a calculator and there's trig involved, you got to be in radian mode. And the reason why is because when we did the initial derivations last week or 2 weeks, I can't remember when we did that. It was probably last week. When we like did all these other like little limits as part of it, those limits only work if you're in radians. So that's why. Or do you have a question or Emma or yeah? Oh, it's not negative. My apologies. My bad. Sorry. You're right. It's not negative. Yeah. So I mean, I obviously can make an adjustment here. Um, I think if I did or divided by, yeah. You see, by doing that adjustment, by dividing by its amplitude, I get back to how it's supposed to be. So you had to do an adjustment as a result. Um, Anyhow, that's what's happening there. Um, the second derivative, that's okay. We'd skip. I think you guys get the idea. So we just skip that. But what will happen is it's not going to get back to its like original configuration, which it would eventually do for the radian mode. So yeah. So
moral is just never
moral, just don't use degrees. Correct. Just don't use degrees. Use radians. Correct. Okay. Okay, new stuff. Before I hand out the new stuff, now for those who are doing their work on a device, if you go to Schoology, click on lecture notes, and you'll see there's a bunch of new stuff like curve sketching, blank worksheet, the filled out notes, derivative exponential log functions, which we're doing today, blank and worksheet, the filled out notes, and then extra practice. We'll get to extra practice next week. And that could be a way to help review for our tests and the stuff. Um, so these are how the notes look. But again, I'm going to hand this out in just a moment. So you have curve sketching, derivative exponential logs, and of course, extra practice of those things. So let me hand out the hard copies of these notes and let's go through it. And we're going to talk about just the basics for exponential logs, and then we're going to hopefully sneak in chain rule into that. I don't know how far I could get with this. These notes are not too long. There's a lot of homework and extra practice problems. Um, I might be able to get to all of it today. We got a 75-minute period, so why not? Then we can enjoy Conjay. All right, look at these notes. Maybe it's not gonna happen until April. Um, I agree.
We definitely
Yeah.
should, that would have been horrible, definitely should have.
Trust me, it's fine.
I'm so glad. Yeah, same.
How would they have solved, how would they have been caught Jared without me announcing it?
Where were you two?
We were at
Um,
Okay, so let's talk about e to the x. Okay, so before I tell you the derivative e to the x, I'm gonna go back to Desmos again, and we'll just graph e to the x, like just see what happens. So e raised to the x power, and I'm gonna adjust because this is really annoying. Let's go -10 to 10. Oh, so much better. Okay, and the step could be 1. Zoom in a little bit. Okay, so you guys know how e to the x looks, right? Pretty obvious. Y y-intercept's 1 because e to the 0 is 1, right? Any to the 0 power is 1. And if I plug in 1 for x, see this is 2 point 2 point whatever, 2.71828. Just like pi, that's an irrational number. It's called Euler's number. Does anyone know how that number came about? Does anyone remember from Mr. Band's class? Like why we have e or where e came from? How e is approximated? Kind of, yeah. It's actually a limiting case. You guys remember this stuff like compounding continuously, compounding?
it's a big confuse.
It involves that. So this is what E equals as x approaches infinity. So if you think about if I do 1 plus 1 over 1,000, I mean, that's a pretty, small fraction, right? But you raise it to what power? So it's a bit of a trade-off. It's kind of like, okay, the fraction gets smaller, but the exponent gets bigger. Or what if I do this? 1 plus 1 over 100 raised to 100th power. It seems that the one up top would be higher than the one down below, but they're actually pretty close together. See, if I just were to punch this in, 1 parentheses 1, damn it, here we go. Sorry, 1 plus 1 over 1,000. Of course, I need parentheses, right? Raised to the 1,000. So you get 2.1769, right? If I change it to 100 and change that to 100, still roughly the same, 2 points. I get 2.704, right? Now, what if I do like 100,000? Something crazy, right? See, it's really close to 2.718. So that's called Euler's number. So it's just this convergence that eventually gets to this number, right? not celebrate as Pi Day, but February 7th is Euler's Day, if you want to call it that. So anyhow, so this is what's going on with E. Now, let's look at it from a calculus perspective. Okay, let's forget about this whole approximation business. Let's look at it from a calculus perspective. What if I drew a bunch of tangent lines? If I drew a bunch of tangent lines, are they positive or negative?
Oh.
And early on, they're pretty shallow, right?
Mhm.
But it gets steeper and steeper and steeper and so forth, right? So aren't the derivatives themselves increasing in value? Aren't they getting steeper, right? So what's happening is that the derivative actually, the values of the derivatives are the same values of the y coordinates of e to the x. So if you were to actually derive this, which we will, the derivative of e to the x is just e to the x. It's the same thing. In fact, actually, if I were to just tell Desmos, graph me this function, d over dx of f of x, it coincides. It's the same thing. So derivative e to the x is e to the x. So one of the easiest derivatives you'll ever see. So it's just e to the x. Um, or if it's a chain rule situation, guys, we write it like that. The derivative of u with respect to x or u prime. So like in this case here, what if I have e to the x squared plus 2? Well, it's e to the x squared plus 2. However, what's the derivative of x squared plus 2? 2x. There you go. Now, how can I do that over here? Well, you did. What's the derivative of x? 1. You've been doing chain rule this whole time without realizing it. Just when it's playing with x, it's just 1. So it's not a big deal. So, and there's an actual formal proof, and we'll talk about that when we get there. So, um, okay. So let's try these problems. So go and try examples 1 and 2, and then we'll do a little summary, and then we'll do another explanation after that. So go and do this really quick. So 1's a chain rule, and 2 is also a chain rule. So what do you get for 1? Yeah, just 5e raised to 5x. How about the next one? E to the x squared plus 3x times what? Yeah, times 2x plus 3. Yeah, you got it. What? 5e. What was that? Exactly. So it's 0, right? You don't worry about it. Now, just one thing to keep in mind as well. E to the x is an exponential function, right? X to the n is a power function. That's why we call the derivative x to the n power rule, right? Like that's 3x squared. So that's a power function. But what if I have 3 to the x? So not dealing with e. What if we change the base to something else, like 3? That's going to be an exponential function. So whatever you do not do this, please. Some people will see this. Don't write this down. This is actually bad. They'll do that, but here's the difference. Your x is an exponent, not the base. If it's a base, it's a power term. It's part of a polynomial. If it's an exponent, it's an exponential function. So this is not true. You can't do that. So what do we do? Here's what you do. And I'll talk about it on the discovery down below. You're going to write 3 to the x, but then times natural log of 3. How come I didn't do that for E? I could have. Well, what's natural log of E? So it doesn't matter. It's redundant, but you could. You could. Technically speaking, the derivative of e to the x is e to the x times natural log of E, but a natural log of E is redundant. So just one. So like, let's look at this one here. 2 to the x, which looks like this, right? Now, if I go to Desmos and graph the derivative of 2 to the x, so that's the beauty about Desmos. I could just easily change this now to like, look at that. Now the black curve is not the same as the red curve. In fact, actually, it's off by some factor, right? Like 0.69. Yes, things seem a little off here, right? Yeah, things seem a tad off. So it's going to look more like this. The derivative of 2 to the x looks like that. And of course, the graphic calculator, you just do d dx, 2 to the x equals x. Now, what if I divided y2 with y1? Let's do this as an exploration. So we'll go back to Desmos. So the fraction here. Okay, so let me turn these off. So what did I just do? I graphed the derivative, the ratio of the derivative to the original function, right? d dx of fx over f of x. What is it producing for me? A straight line. And if you think about it, what are the y-coordinates of all these straight lines? 0.693, right? That was precisely what I got for my y-intercept for the derivative, right? Okay. Well, if I think about it, natural log of 2, is that log base c of 2? So basically you're saying log base c of 2. Well, now what is that approximately? If I said equal to x, 2 equals e to the x power. E is 2.718. You're setting equal to 2. So x is going to be less than 1 to make that work. In fact, actually, if I were to do natural log of 2, I get 0.693. By the way, that also comes from Half-Life too. If anyone's done Half-Life, you may have seen that. So essentially what's happening is that the ratio between these two is actually more like this. Or natural log of 2. So when you compare the derivative to the original function, the derivative has one little extra thing, has that natural log. So this right here is 2 to the x times natural log of 2. So when I actually divide y2 by y1, I'm doing 2 to the x times natural log of 2 over 2 to the x. See those cancel?
Mm.
You get natural log of 2. So the discovery helps us to see that. Again, there's a form derivation that goes with it. We'll get there if we have a chance. So that's what's happening. 2 to the x times natural log of 2. Can we move on to the next page? So analytically, let's see what's happening here. Okay, and this one I kind of I'm going to show you the filled out version because I actually kind of botch this derivation sometimes. So let me show you the filled out version and I'll walk you guys through it. I just want to be honest, I haven't seen the derivation. I haven't done a derivation in a few years, so I'm a little rusty. And I don't feel comfortable doing on the whim. So I'm going to show you the derivation. Then we'll have a discussion as why it works the way it does. Okay. So let's go off to the right. Look at the box off to the right. See it? What if you took a natural log of both sides? And what a to the x equal e to the p. Fine, whatever. They're both exponential terms, right? A to the x equals e to the p. So you take natural log of both sides. Now, if you take natural log of both sides, and actually I'll do this now I kind of know what's going on here. I think I can handle from scratch now. Now I remember what to do. So we'll take natural log of both sides. Does that make sense what I'm doing in the next line? What rule is that called? What property of logs is that? You guys remember what that rule's called? Power property?
Mhm.
Yeah, power property. Yeah, so this is a hypothetical. We're hypothetically saying that's true, which is fine. They're both exponential terms, not a big deal. A to the x equals e to the p. Then you take the ln of both sides. And then you use the power property. And I want to take a guess what's the next thing's going to happen. Oh, you're right. Yikes. Thank you, Marie, for catching that. 100% correct. Thank you. And it look weird. What do you think happens next? Yeah, ln e is 1. So a to the x equals e x times natural log of a. So you come back here, you're going to say this. So this is just a rewrite.
How do we get to,
Because we deliberately set a to the x equal to e to the p. Yeah, because remember, a to the x, we hypothetically said that a to the x equals e to the p. And when I solve for p, I got x ln a. So a to the x equals ex ln a. That's what I'm doing. I'm substituting. That's a rewrite. You don't. That's what I'm telling you. That's why I look up because I forgot. It's not anything you have to do on a test. Don't worry about that. I'm just trying to show you why this derivative works the way it does. That's all I'm trying to do here. At this point, it should be pretty smooth sailing because what's the derivative of e to whatever? E to whatever, right? But then you got to do a chain rule. So this is part of a chain rule, right? And ln a is just a constant next to x. What's the derivative? What if you have any constant times x? What's that derivative going to be? Just that constant, exactly, right? So So then you got this. Y prime is EX ln A times ln A. And then you could bring back what is EX ln A, what was that to begin with? A to the X or E to the P. But we'll use A to the X. And so it just gets you back tested. The whole E thing was more of a bridge. So it's A to the X times natural log of A. That's a formal proof for A to the X. If you have U, great, fine, whatever. But then you have to consider doing the chain rule for the U part, which is du over dx. If we have that. So that's all you're doing. So you take natural log of both sides. If you want to go through the formal proof of it, but again, nothing I'll test you on, just in case you know why. That's why. I mean, of course, we saw it graphically as well. We saw that, right? Like, oh, okay, if I'm graphing, it's not the same thing. They're off by a factor of ln A. So for example 3, it's pretty straightforward now. That's gonna be 10 to the x times what? 10. Done. That's it. Let's look at 4. There'll be 5 secant x times what? Natural log of 5 times what? Yeah, secant x tan x. Yeah, there you go. Because that's chain rule. This is an extra example we just decided to throw in there. Well, what the heck? Let's just do that. Why don't you guys figure that one out, and let me get my cord, and you guys can tell me in a minute what you guys get. Yeah, that might have been a.
I think that's the next example.
Oh, is that the next example?
Scroll down.
Oh, let's do it. What you got? Do it.
Example 5.
Oh yeah, so that was the whole formatting issue. Okay, so you should get 7 raised that junk times natural log of 7. What's that truly going to be? Plus cos x? Okay, there you go. All right, next up. Ah, I've not taught you guys implicit differentiation. I just realized that's going to be a slight issue. I'm just going to give you the formula. The derivative of this, I'll just tell you right now, is just 1 over x. I'll just give it to you. Yeah, there's another differentiation technique called implicit differentiation, which is kind of an extension of the chain rule, but I'm not supposed to do that. I'm supposed to say that for BC. I'll just tell you the derivative. It's just 1 over x. It's real easy. That one I'll just kind of get too straight up. Or it's 1 over u. And why does that make sense? Because if you look at the natural, you guys remember how the graph of log looks? So I'm kind of giving you guys a bit of a crash refresher, if you want to call it that, on logs today, as well as exponential functions. What's the x-intercept for that, by the way? It's one, yeah. Mhm. Now, if you graph, if you draw the tangent line, right? If you draw all these tangent lines here, are tangent lines positive or negative? They're positive, yeah. But initially, they're really steep, and they get less steep as x gets bigger, which makes sense why you have 1 over x. And also, if you have like a fraction, like let's say x is like zero point 0.1, of course it's going to be pretty steep. It'll be like 10, right? Or 0.01 would be 100, and so forth. So they're very steep when x is less than 1, but it gets more shallow when x is bigger than 1. Do you guys see the trade-off there? Okay. And it's still a chain rule we have to deal with anyway, but the formal proof, because we haven't talked about implicit differentiation, let's not worry about it. Okay, and then I'll show you what's happening with log base AX, and we'll do more examples. So for example 6, you're just going to say this. Y prime is 1 over 7x times what's the root of 7x?
Uh,
So actually it's kind of interesting because it gets back to what?
One over X.
Yeah.
Hmm.
Is that a coincidence or is that meant to be? So log properties, guys. So you're getting a crash course in log properties right now. Do you guys remember log properties?
Kinda.
Like I won't tell them to span. So this is the product property for logs when you have two things being multiplied to get that.
Mhm.
And then if you take a derivative, what's derivative of a constant?
Zero.
And derivative of ln x right now is 1 over x. So actually it doesn't matter. If you have a constant being multiplied to x, you're always going to get back to 1 over x. So it is meant to be because of the product property. Now, of course, you have like x squared or there's some other junk. Of course, you do your chain rule as part of it. Okay, any questions so far? Doing okay? All right, let's keep on moving. I just feel bad for you guys. You have another class after this. Ugh. I should have got you guys some like snacks or something. Well, I am doing pies.
Hi there.
Yeah, and it'll be leftover pies. No, 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 no. But I'm gonna be baking Thursday morning, unless it's Kanye. But but anyway, that's the plan, and I'll have pies for you guys. So keep you guys going.
The worst excuse.
I don't know.
Or no, wait. Yeah, no, I was supposed to work five. Should be 14 minutes.
It's a day early, yeah. It's a day early.
Yeah. Well, it come out on Friday. I don't know. But it was Friday.
Maybe they come out on the.
Okay. In case you guys forgot, change the base formula. I know you guys covered this, but you probably forgot. If you have some base that's not plain old 10 or E or whatever, something weird, really weird, you can express it this way. ln x over ln a. In fact, actually, you can do any base you want. You do like log base of like 1.23 x over log base 1.23 of a. It doesn't matter. The change of base formula says this. Log ax equals ln x over ln a. Or you do log, common log. Or you can do any base you want. It's totally up to you. Like log of 1.23x. Whatever your little heart desires, whatever base you want to do, as long as bases are the same. By the way, like I'm not sure if I showed you guys something called a slide rule, like the precursor to the graphing calculator, scientific calculator. My father had one, probably your grandparents, because I'm probably the same as your parents. Um, but that's how when you had to do like really crazy base, like really logs of crazy bases, you actually had to do this first and then look up the tables for common logs of all these different values. Like if you want to do like log base 2 of 3, you didn't have a fancy calculator 40, 50 years ago to do that. You actually had to do log 3 over log 2. And he had a table of values where you looked up what log 3 was and looked at what log 2 is, and you divide those two together. That's what you had to do.
Times table, like the base is.
Correct. Correct. Right. So, so that's what's happening here. So now if I want this derivative, well, the derivative's not going to be so bad. That's just going to be 1 over natural log of A times 1 over X. And why is that? Because isn't this ln A just a constant? Or is it a constant being multiplied or divided? Divided. That's why you push it off to the side. If you push it off to the side, it's 1 over ln A. That's a constant, mind you, times natural log of X. And what do we do about constant multiples? They come along for the ride, for the derivative, right? So 1 over ln A stays in the derivative, but now you focus on ln X. Derivative of ln X, we know is 1 over X. And that's what you get. So it's 1 over ln A times 1 over X. Or if it's a chain rule situation, fine, 1 over ln A times 1 over U, and whatever the derivative of U is with respect to X. Like let's say you got like a cosine or sine or some weird, really weird stuff, right? Fine, deal with it. So that's just part of chain rule. Okay, I'm gonna have you guys try example 7 and 8. Try on your own. See how it goes. We're gonna revisit the power rule, which is gonna be super easy. Rest of that should go by pretty fast. Just make sure we're on the right track. Do you guys get that for number 7?
Yeah.
Yeah, you can clean it up too. You actually should clean it up because you're doing 1 over ln of the base times 1 over the inside of the function. And then also you got to do a chain rule. And that 1 over x squared is x to -2. I didn't change that initially, but I felt like changing for derivative because that helps me to figure that out using the power rule. And then I get that. Or for example 8, y prime. What's the base if you don't see a base? So do 1 over natural log of 10. So it's the opposite of exponential function. 1 over sine x. And derivative of sine x is cos x. So you should get y prime equal, and 1 over sine is cosecant. Or actually, I could just say this. What's cosine over sine? You guys know this. Yeah, the tangent, right? Yeah, so you get that. Okay. Okay, next up. Um, why does the power rule work the way it does? Like, what's the formal proof for it? Because I just kind of we just assume it works and it makes sense, right? kind of saw these patterns. We did do the limit definition for all these different power terms like x squared and x cubed and whatnot. But here's the real reason why it works. So I'm going to show you guys the filled out version because again, I kind of forget this stuff sometimes. So um, here we go. Um, yeah, let me do a little work off to the side here for you guys. Okay. Um, let's focus on the dialog box first. You have x equals e to the p. So kind of the same thing we did before for the derivation of e to the x. So let's do the same thing here. Uh, take natural log both sides. So far, okay with that? So p equals this. So we're letting x and equal e to the p. Again, that's you could totally do that. Like, for example, probably not really aware, but if I do 2 to the fourth power equals 4 to the p power, what would p equal to make that work? If 2 to the 4 equals 4 to the p, what is p in this case?
2.
2, right. You could totally rewrite any power with a change of base. You just change the exponent. You totally could do that. So letting x n equal e to the p, who cares? Doesn't matter, right? It's not a big deal. So if I do that, remember p is n ln x, right? We know this. Now, if I do that derivative, what's derivative e? E to whatever, right? And I also have to do the derivative of the exponent itself. And by the way, you could totally do this. Really loud. Really, I don't know what's going on. Let me make sure I'm doing this right. Hold on a sec. Ah, okay. I kind of messed up a little bit. Hold on a sec. Okay. I made a little mistake, guys. I caught myself in this one. Okay. So, made a little slight error. Easy fix. Easy. If you guys are confused, you should be, because that made no sense what I just wrote. Yeah, I was supposed to do that, right? Because if you think about it, that's the same thing, right? E to the n ln x power is the same as e to the ln x raised to the n. Because, for example, I have 2 to the 5 times 3. Isn't that just 2 to the fifth and raised to the 3? Right? So you totally could do that. Now, what's e to the ln x, guys? What was the e and ln? They knock each other out, so you get x. And if you think about it, That's times n times x in -1 power. And what do you get? You get the power rule. Pretty nifty, huh? Because we know derivative ln x is 1 over x. And when I use my properties of exponents and combine things correctly, you get that. So that's why the power rule works the way it does. So that's the formal proof that goes into it. I think it was an extra credit question you guys want. I don't care. None actually. But I care more about the mechanics. That's what I care more about. So now in this case, it's pretty straightforward at this point, right? Like, well, yeah, you can do this for any real number. What's that derivative going to be for example 9? Where's the root 3 go, guys? The front, x raised to the root 3 minus 1. Or here, that's 5 pi over 2 moved to the front, 5 pi plus 2. And then subtract the exponent by 1. Five p plus 1. Okay. So what do you guys think about example 11?
First from the derivative
Yeah.
to
Well, hold on. We want to be perpendicular to y equals -1/3 x plus 2. So what's this what's the perpendicular slope for that?
Yeah.
3, right? Then you're right, Charlie. We want to find that derivative, which is that. So 3. Yeah. And I don't feel like finding the y value for that, so we'll just leave it as the x coordinate. But hopefully you can see that, okay, I know I find a slope. I know slope represent, and I want at what point in the graph of this is the tangent line? Yeah, and so I need 3 as my slope, obviously. So hope that's okay for that one. Okay, let's look at example 12. And we'll go and stop there because I know you guys are pretty spent. So that's good because we can talk about the next page, last page on Thursday. So take a quick look at example 12. Give you guys a few minutes to work on that, and then we'll wrap up. And I'll tell you your homework will be after that. So take a look at example 12.
And Jack, the one on the chair. He's like the big instruction.
Yeah. Yep. Yep.
Hard to make calculate. Actually,
Absolutely.
And then use it though.
You go outside.
How would you? What was 0.98 of was oh. Oh no, mine is.
These are calculator.
You need a calculator.
Yeah. So 3 days. 400. This doesn't. It's 4 minutes, so it's 7 minutes.
By the way, I was trying to suggest that you guys go to y equals, store the equation under there, and then use alpha trace to keep calling back y1. That way we don't have excuse me, I'll lose my voice. You don't have to keep like replugging the function. How many people were infected initially? Just one. Yeah, it was like 0.989. How about after 1 day? Roughly 3 people. We'll round to the nearest whole number. Or round up. 3 days? 19 people. Sorry, just 2 days. No, it was 3 days. Sorry. Yikes. Wrote that wrong. Yeah, you can see like people tend to get sick pretty easily, right? Like someone, we'll say Charlie comes here sick, gets me sick, and I get you guys sick, and then also the whole class is sick, right? Sorry, picking on you, Charlie. I know you'd stay home. How many people get sick after the 6th day? 200 people, right? Crazy, right? So clearly there's a rapid increase. Okay, there's a rapid increase. This is actually what we call a logistic function. And COVID was kind of this way. They tell the flattening of the curve. Well, that's you want herd immunity, right? You want everyone to get sick, so everyone gets the disease. So how fast is it spreading? So that's where we have to find the derivative, p prime of t. Now, by the way, before I get too carried away with this, can I use product rule? Or sorry, can I use quotient rule or chain rule or either? Yeah, you could do either. You could rewrite the function like this.
He's a number.
And then times at the inside, which is going to be so we would want you to do this in person. I mean, sorry, by hand. Um, so it'll look kind of like this. But you could just use your calculator too, right? But you should be pretty comfortable doing this by hand.
Yeah.
But I could just, yeah, again, hit alpha trace or alpha window and derive alpha trace y1 x equals 3. So what do you get for how fast to spray after 13 days after 3 days? Yeah. 18 students per day. So on average, after the third day, you're noticing this is the infection rate. Like, oh wow, this is wiping out an entire section, right? 18 students. But the rate's gonna be pretty rapid as we get to 6 days. On average, how many students are getting sick per day? 100. So we expect the entire school to get sick pretty darn fast once we reach that point. And that's because that part of the curve is very steep. It's very, very steep at that point. So
sorry.
very good. Okay, so we're gonna stop there. So you can see how we're using chain rule, we're using quotient rule or product rule or whatever with the exponentials. So homework's gonna be this. Looking at the packet. We'll use proof for next time. Yeah, it's gonna be page 7, 1 through 10. So you're just doing 1 through 10 on page 7 of this packet. There's more stuff afterwards, but we could do that later. And maybe what I might do, I might pump the brakes a little bit at the end of the week because these are long weeks, and if there is no G period on Friday, then I don't feel so bad teaching new. So I might not teach new material. We'll just do some practice problems and eat some pie.
We'll do proofs though, right? We'll finish this.
Oh yeah, we'll finish this, of course, yeah.
Okay.
But by the way, this is our schedule 3 or 4 years ago. We had 75-minute classes like this. Oh yeah. So it's training. I'm with you guys. Yeah, it alternates between 3 and 4. Yeah,
Like every week.
yeah, pretty much. Yeah.
Like a 5-day class.
Yeah, we still have 5-day weeks, so yeah. No, 4. Yeah. But we had to have a schedule that can easily switch to Zoom if we have some variant code, like when we have like Delta or Omicron. Yeah, so we had to be able to go back and forth between Zoom. See you guys.